Welcome to today's central exercise class. We'll be discussing sheet number 3 today. And as usual, you're invited to join us on our chat channel to ask your questions. The chat channel is available here on chat.tum.de. And please use this channel here, MA9714-CE, to post your questions. As usual, the chat will be moderated, and today's moderators, once again, Alit Carson.
So now your screen sharing stopped working. Is that on purpose?
I'll switch it back on in just a second. Before we start, a quick note. So as you know, in addition to this central exercise class, we also have tutorials every Thursday, starting at 2 o'clock for 3 hours, and you're welcome to join us there. As there have been questions in that direction, I'd like to stress that you can ask any type of question in the tutorials. So they're not limited to one particular exercise sheet. Of course, you are welcome to ask questions about the current and the previous exercise sheet, but we'll try to answer any type of questions you might have in the tutorial classes. So join us. You don't have to be there at 2. You can come and go basically whenever you like in that 3-hour period. We'll assign you to breakout rooms, so you're also welcome to join as a team, where you can then discuss the problems among yourselves and just call for help whenever you need some tutor to help you. Right? So we'll be happy if some more people can join us there, so that we hopefully be able to help you and answer your questions. Good. So let's restart the screen sharing. So that hopefully we can discuss sheet number 3 now. So the first question on sheet number 3, let me just quickly show you that sheet here, this here. So there's 3 functions and a couple of plots, basically 2 types of plots that are given here. One are surface plots, where these are all functions from R2 to R. And the idea here is to regard the x1, x2 plane this here as the coordinate plane. And to each point of that plane, we assign the value of the function as the 3rd coordinate in that direction here. And so that yields a surface like this here, or that. And as an alternative, we also have contour plots. The last 3 plots here are contour plots, or level set plots. The idea here is to determine for a given value all combinations of x1 and x2 that map to that value. So what we basically do is we cut through those surface plots at certain levels, right? So we fix a value, like for example 0 here, and then we take the plane at that level, we cut through that surface here. And in this case, the cut will be a line like that. And that is the level set that corresponds to that value of 0. And that's one of the lines we draw into the level set. And the level set consists of all those lines, all those curves for a number of levels. And the question here in this problem is, which of these surface plots and which of these contour plots belongs to which of these 3 functions here? So let's try to answer that question. This is C31. So in this case, we have 3 different functions. Let me write those down once again. So f1 of x1, x2, that's the function x1 plus 1 squared minus x2 minus 2 squared. F2 is the function minus x1 plus x2. And f3 is the function x1 plus 2 squared minus 2x2. So basically, if you look at those functions, you can already gain some insight on how they behave. So in this case, basically we have a combination of 2 more or less independent quadratic functions. So there's a quadratic function that only contains x1, and here's a quadratic function that only contains x2, right? So if you look at this function along x1, keep x2 constant just along the x1 axis, then it will behave pretty much like a quadratic function. And the same is true if you fix an x1 coordinate and then look into x2 direction. Again, it will behave like a quadratic function. If you look at the signs, you can see that the quadratic function here for the x1 that has a positive sign before the x1 squared. So that will look like this, parabolas that are open above. And here in the x2 case, you have a minus sign, so that will yield a minus x2 squared. And that means on a global scale, more or less, the function looks like parabolas that are open below, like this here. Right, so that's basically how f1 will look like. And let's have a look at the plots and see which one of these might be a good fit. We can look at that sheet here. There's nothing that looks like a parabola in this plot here, so we can probably exclude that. Things are different in that plot and in that plot. So here we have something that looks like a parabola here, right? So if we move in this direction for any fixed value of x2, we get a parabola. However, if we fix a value for x1, for example, -2 here, and then walk in x2 direction, in this direction here, the function basically looks like just a line, more or less, right? So it's probably not the one we want. Let's look at this one here. So if we, again, fix some x2 coordinate, 0, for example, and then walk along that line here in x1 direction, what does the function look like? So if we cut through that plane here, basically what we get will be some parabola that basically looks like this, right? Like this, depending on the x2 level that we have. And if we fix one of the x1 values, for example, if we fix this here at 2 and then walk along that line in x2 direction, we again get something that looks like a parabola, like this, right? The lines here are bent along that surface. So what we get is in x1 direction, parabolas that are open above, and in x2 direction, parabolas that are open below. So this here is exactly the plot that would correspond to the first function, to the x1 function. Okay, so let's take that one first. Try to copy that. There it is. Right, so that function here, we already said basically the plot that corresponds to that one is, let's see, this was the right one, yeah? Again, because basically we can see in that plot, here's the parabolas in x1 direction, and here's the parabolas in x2 direction, and they bend the right way. So that among all those three choices, that must be the plot that we're looking for. As for the contour plots, let's see if we can find that as well. What would we expect here? Well, if we take a cut at one given level, so level means we were fixing one of the x3 coordinates now, and we look at all x1, x2 combinations that yield exactly that function value. So we cut that surface by a plane that is parallel to the x1, x2 plane. And we look at the lines, at the curves that are cut out from the surface by this plane here. What do we get? You can draw this here. So basically, that's the plane that we're taking. Now, if we cut that through, we'd expect to get some curves like that and curves like that are all on the same level, on the same height of that function. So if we now look at the plots that we have here, well, that's probably not the right one, right? We expect the curves to be bent in some way. It would not be straight lines. Here we have bent lines, parabolas. But again, that's not what we expected because of that saddle-like look here, right? So we would expect something like this and this. So curvature is different if we look at the same that surface from a different direction. So the only thing that looks close to this is this third plot here. Yeah? Here we have these lines and these lines. So that's typically for what we call a saddle point, basically a point where you have a direction where the graph, the surface decreases and one where it increases. That's a saddle point. And the surface, the contour plot for a saddle point looks something like that here. So let's add that as well. Let's see, that is this one here. Okay, so let me add that looks like a saddle. And in fact, a point like that here in the middle, that's what we call a saddle point. We'll revisit that term later and we'll define it more precisely later on. Okay, so that's the first function. Now for the second one, this one here, that's probably the easiest of all. If you look at that one, you can see that has an x1 term and an x2 term. One is negative, one is positive, and they are linear. So that means the function will grow linearly in x2 and will decrease linearly in x1. So again, if we look at our choices for the surface plots here, well, the first one seems to be a good fit, right? So if x1 increases for a fixed x2, then the function value here along that surface will decrease. If x2 increases for a fixed x1 value like this here, the function value will increase linearly, right? So that's a plane in three-dimensional space. That's exactly the function we need here. So the right fit is this plot here, this function. And again, that is a plane in R3. And for the level sets, well, basically we're looking for all combinations of x1 and x2 that correspond to a fixed level, so that this value minus x1 plus x2 is 0 or 1 or 7 or 5 or whatever. And obviously that means we are solving a system of linear equations, one linear equation actually with two variables. And the solution set for that, you know how that looks like. It's just a line. So the only lines we have here are in this plot. So that's obviously the one we're looking for. Right, so let's insert that. So this here is the corresponding contour plot. Right, and you, of course, you notice that level 0 is missing here. Of course, there is also a line for level 0 that will look like this. Right, so that corresponds to level 0. Basically, where x1 equals x2, remember we have that equation here. If you want level 0, that is the same thing as x1 equals x2. And that's exactly this line here. And for other levels, x1 is, for example, exactly 1 or 3 or 5 greater than x2 and so on. Well, that of course solves the riddle of the third one. So let's have a look at that as well. Now this function here, it's basically a combination of the ones we've just seen. Again, we have this quadratic term here that depends on x1 only. So if we vary just x1 and keep x2 constant, that function will look like a parabola, positive sign. So it will look like a parabola that opens above like this. In x2 direction, this is just a linear term, a negative linear term. So the function for constant x1 values, the function will decrease linearly as x2 increases and vice versa. And again, looking at those graphs here, what do we have here? Well, we need a function that is basically a line, a falling line in x2 direction. And if you look here, you can see that. Yeah, well, that's exactly what that surface here does. We have lines here along x2 direction. And if you fix x2 and look at that function in x1 direction, it looks like a parabola. So that's exactly the plot we want here. So let's insert that one. And of course, if you look at the level sets, you can easily see this one remaining level set here is the one that we need. So again, we want all combinations of x1 and x2 that yield the same function value. So we cut through this surface here along a certain plane that is parallel to the x1, x2 plane. What we get if we do this are these parabolas here that we're looking at. Right, so that will be the corresponding contour line plot. Okay, so that should hopefully equip you for finding contour plots and surface plots for functions, or getting a rough idea of what a function may look like from the definition. Of course, those were all pretty easy cases, and the distinction should be pretty clear. That can, of course, be made more complex and more complicated, but I hope you got the basic ideas of getting an idea of how a function looks like. Okay, questions?
So the only question I have is what the lines really indicate. So the lines in the contour plots. I mean, you have said it, but maybe it doesn't hurt to say it again.
Okay, so what the lines in the contour plots indicate, let's look at that one. It's the easiest one that we have. Basically, each line corresponds to a level. Level set, and that means a level set that's all combinations of x1 and x2 in the coordinate plane, where the function value, in this case of x2, is equal to a constant value. Let's call it alpha. So that is the level set of f for the level alpha. And basically that means we're looking at all combinations that yield the same constant function value. And we just choose different values of alpha here. And for each alpha, we get a line or several lines or curves. And those are the curves that we draw into the plane. And often we also write a number next to those. That number would be the level, right? So here, for example, this one, that is the line where the function value is 0. And remember the definition of the function. So f2 of x1, x2 is defined as minus x1 plus x2. And if we're looking for all combinations of x1, x2 where that function value is 0, that means we solve this equation here. And well, that is solved exactly if x1 is equal to x2, and x2 is a free variable. And the line corresponding to these two combinations here is exactly this one here. And for example, different example here, if we take that orange one here, if we look for all combinations of x1, x2, where the function value is 1, for example, well, what that means is minus x2 plus minus x1 plus x2 is 1. So in other words, we again have a system of linear equations, one equation with two variables that we can easily solve. So that would mean x1 is equal to x2 minus 1. And well, where can we find that? Just look at that plane and we can see the level set for 1 is this line here, right? Maybe that's a unusual way of putting things. I should rather solve that for x2. That's probably something you're more used to. That will be x1 plus 1, right? So here's the x2 axis. So if you regard this as a function of x1, That means you have a slope of exactly 1. So that's parallel to this first line here. And it's shifted 1 in x2 direction like this. So this is the correct line here, right? That's the level set corresponding to the level 1. As I said, we just draw a couple of those level sets, and that's the contour plot.
That was the only thing I had. So no more questions.
Good. So let's move on to 3.2 then. Now, 3.2 is about sets, in this case, in the plane, or in more general, and in the R to the n. Here we have a set, it's called S, that consists of all points in the plane that satisfy x1 plus x2 squared is less or equal to 4. The question is, how does that set look? Can we draw that? Can we sketch that? What is the interior? What are the boundary points? Is that set open? Is it closed? Neither or both? And is it bounded and or compact? Okay, let's start with the sketch. If possible, I'd always try to solve the equality case first. So in this case, we have an inequality, less or equal to 4. Well, let's first look at the points that fulfill this with equality. And that's probably easy to find all those where the less or equal to holds. It should be easy to solve this for x1, because x1 does just appear as it is, right? Without any function applied to it. So x1 plus x2 squared equals 4 if and only if x1 equals 4 minus x2 squared. So what does that mean? Can we draw the set? Well, this is almost a functional equation as once you're used to. We have a function that is quadratic in x2, basically a parabola that opens like this here with a shift of +4, right? The only unusual thing is that we solve this for x1. Usually you solve for x2, and then you can just draw the function. That's a little more complex here. You can also do that, of course, with the case distinction, but solving for x1 is a little easier. You just have to, at least in your mind, turn around the coding system, right? So now the free variable is the x2, and the dependent variable is the x1. So let's try to draw this. Sketch a coordinate system here. So as usual, we have x1 on this axis and x2 on that axis here. Now, again, we vary the x2. So this is our variable axis now, and we then draw the function value above that or below that line. So here's the positive values here and the negative values in that direction. This is, again, a parabola that's opened like this. So it opens below. Below means it opens in that direction here, in the direction of negative x1 values, right? And the apex is, well, if you forget about that 4, the apex would be exactly here at the origin. And now it's shifted by +4 in x1 direction. So let's see where that point is. 1, 2, 3, 4. That's here. So that is the apex of our parabola. And its roots, so it passes the x2 axis exactly at the points 2 and -2, right? Because that is where x1 would be 0. And if I want x1 to be 0, then x2 squared has to be 4. And that means x2 is either 2 or -2, right? So I know this, and I know this point, and I know it's a parabola. So I can try and sketch that very roughly. Let's see. Very roughly should look like this. Okay, so that is the set of points x1, x2, where this holds at equality. So now what about the inequality that we have here? So again, if we solve for this with the inequality, we get something like x1 is less or equal to 4 minus x2 squared. 4 minus x2 squared, that is the parabola. So x1 is less or equal to the line given by that parabola. And that means x1 is somewhere in there. Right? So those are the admissible values here. And that means this is the set S that we're given here. Now, what about interior points, boundary points? Remember, an interior point means if I have this point, I can draw a small disk around that point that is still contained completely in the set. Points with that property are called interior points, where I can choose the size of the disk arbitrarily small. There must be some disk such that it works, but I can make that as small as necessary. And of course, that holds for all the points that are somewhere in that area. This one, for example, I can draw a disk around that, or I can draw a rather large disk here around that point. This one here will work. So all of these are interior points, obviously. It does not hold anymore for points on that line here, like this one, because for every disk I draw around this point, there'll always be points in the interior, so in the set S, and there will be points outside of the set S. So those are outside of S. Those are in S. No matter how small I make that disk, right? There's always points inside and outside of S in such a disk. So this is not an interior point, but this property is the defining property of what we call a boundary point. For every disk I draw around the boundary point, there's always points inside of S and points outside of S contained in that disk, no matter how large or small I make that. So points on the line are the boundary points of that set, and points that are inside of that parabola, excluding the line, are the interior points. Right? So interior points are all those. I usually draw excluded lines as dashed lines. Right? So these are the interior points of S. And the boundary points, let's draw those as, let's say, blue. I haven't used blue yet. Those are the boundary points here. Okay, so that's the boundary of our set S. Okay, before we move on, any questions already?
No.
Good. So now the next question is the set open or closed or neither of those? It's part B. That was actually part A here. Well, it's easy to answer. An open set simply means all points in the set are interior points. The set consists entirely of interior points. All points in set are interior points. That is not the case here, because all those boundary points on that line are not interior points, right? And they are contained in S by definition. So that's not open. S is not open. What about closed? For closed sets, the definition was the inverse is open. So if we take R to the n, or 2 in this case, and subtract the original set, take that out, then the remaining set needs to be open. And the original set was closed, so open and closed. In that way, they're inverses to each other. Or we could also say for a closed set, we want it to contain all of its boundary points. So it's closed if it contains all of its boundary points. The boundary points is the blue line here. And that blue line is, of course, contained in S. There's no other boundary points. So S is, in fact, a closed set. Okay, so that means this set contains all boundary points. That's the case here. So S is closed. And open and closed are not mutually exclusive, right? It could have been true that the set S is neither open nor closed. And there are even sets that are both open and closed, right? So you cannot conclude the set is not open, so it must be closed. That's not true at all. So the set is not open, but it is closed in this problem setting here. And the last question is it bounded or compact? And compact possibly. Let's answer that one as well. So part C, bounded. Bounded basically means there is some infinite disk, or in general, some infinite ball, finite ball, finite disk, finite ball, that contains the set. And by finite ball, I mean a ball of finite radius. Is that the case here? So usually you draw those balls around the origin, but it doesn't really matter what you choose. If I draw a ball around the origin, that has to contain the whole set, then of course the radius has to be at least 4, because I need to include that point here. So I can't go any smaller than that. Let's see if I draw something like that ball here, then you can already see there is a part of that set that is outside of the ball, so it doesn't contain the whole set. Now, of course, I can blow up that ball, but no matter how large I make it, right, there'll always be points in that set that are outside of the ball because it continues infinitely, in this case here, in that direction, or on the left, in that direction. Yeah? That whole negative x1 axis is contained in the set. So no matter how large I make that yellow ball, there'll always be points in the set outside of that ball. So S is not bounded. And finally, question, is it compact? Now, compact is just a handy abbreviation for closed and bounded. So in this case, the set is closed, yes, but it's not bounded. So it's not both. And that means S is not compact either. Okay, so closed set, not open, not bounded, not compact. Questions?
So one question, how do you know that you have to draw 3-dimensional pictures in the first exercise, and here you only drew 2-dimensional pictures?
Mostly because that's in the problem statement. So if you look at that, here in the first exercise, we want to do surface plots of those functions, and those functions have a two-dimensional coordinate space and a real function value, one-dimensional function value. So a surface plot consists of all combinations of coordinates. So those would be two coordinates plus the function value. So those are points in 3D space. The level sets, in contrast to this, only live in coordinate space. So those would be two-dimensional curves like this here. And in that case, the set S consists of points with two coordinates in R2. That's explicitly given here. So that set lives in R2, obviously. There's no function associated to that, at least not right now. I hope that answers the question.
Yeah, that was the only one I've seen. So
okay. So let's go ahead to the last problem on that sheet. C33. That's basically an exercise in diagonalization once again, an application, an interesting one, I think. You remember that we've discussed the Fibonacci sequence briefly in Math 1, and we also talked about it in Math 2 in the lecture videos. The Fibonacci sequence is defined recursively. The first two elements are given as 0 and 1. And then the definition just extends that by saying, well, the k plus first element is simply the sum of the two preceding elements. So fk plus fk minus 1. And of course, that can also be written as a vector matrix equation. So the idea here is simply to say, well, I have this sequence fk/gk of a 2D sequence of vectors with two coordinates. And I define that again recursively by saying f1g1 is defined as 1, 0. And fk plus 1, gk plus 1 is defined as, well, the first is defined as fk plus gk, and the second is defined as fk. So basically, you can see that this g here is playing almost the same role as f, but the index is one below, right? So gk is in the Fibonacci sequence always the predecessor of fk. And that's exactly what is in this second equation here. Gk plus 1 is then fk. Gk will be fk minus 1. And this first line here, that captures the definition, the recursive definition of the Fibonacci sequence, fk plus 1 equals fk plus gk. And remember, gk is fk minus 1. Okay. And that can neatly be written down as a matrix vector equation if you just use the following matrix. So we need to multiply a matrix with fk, gk. The first row would then be 1, 1, fk plus gk, and the second row would be 1, 0, just fk, no gk. And this is what we call the matrix A. So if we have that form, well, what do we gain from that? First thing that we gain is we can more or less directly compute the nth element of that sequence, fn/gn, without going through all these recursions. Basically by saying, well, this is A times fn minus 1 gn minus 1. And we know that fn minus 1 gn minus 1 is A times fn minus 2 gn minus 2. So this is A squared fn minus 2 gn minus 2. And we can go on. This is A squared times A times fn minus 3, right? Gn minus 3. So a to the power of 3, fn minus 3, gn minus 3. And so on. And of course, if we repeat this until we arrive at f1 and g1, you can easily see that we need to do this until we get the n minus first power of a here, right? So basically, the power of a corresponds to what we subtract here. And to get to 1 from n, we need to subtract n minus 1. Yeah, so that's the power that we need here. That doesn't help a lot yet, because basically we've just moved the recursion elsewhere, right? Before we had this recursion in the f's, and now we need to compute this power of a, which means we take a times a, then multiply that by a, then by a, and so on until we have done this n minus 1 times. So that's not really different from the recursion we had before. It's just, it happens at with a different object. But that's basically all there is to it. So the question is there a way to compute this a to the n minus 1 efficiently? And if we can do this, then this here will yield an explicit formula for fn and gn. So instead of having to compute the Fibonacci numbers recursively, we could now apply that explicit formula and compute any Fibonacci number we want directly. And that's exactly what will happen in B and C. Before we do these, any questions already?
No questions so far.
You're awfully quiet today.
Yep.
Is this just too easy?
Well, you're doing a good job explaining.
Maybe it's too complicated. So if one of those is the case, please don't hesitate to just speak up. Okay, so that was part A, basically. Let's have a look at part B. So the setup for computing this power efficiently is basically diagonalizing the matrix A. And that's what we'll set up in part B, where we determine the eigenvalues and the eigenvectors of A. It's not a particularly complicated matrix, so that should be easy. Let's start with the eigenvalues. We want the characteristic polynomial of A, PA of lambda. That's the determinant of A minus lambda I2. Or so A is this matrix here. And we need to subtract lambda on the diagonal. So we want the determinant of this matrix, which is, let's see, we get lambda times 1 minus lambda, oh, sorry, minus lambda times 1 minus lambda, like this, minus 1. Or let's see, that's lambda squared minus lambda minus 1. And the roots of that characteristic polynomial are going to be the eigenvalues. So we need to find all lambda values where this is going to be 0. And we can compute this by simply using the quadratic formula. So let's see, that's minus 1, that's plus 1, plus minus the square root of 1 plus 4 times 1, so that's 4 divided by 2. So we get 1 plus minus the square root of 5 over 2. So those are the eigenvalues of our matrix A. Lambda 1 is 1 plus square root of 5 over 2. Lambda 2 is 1 minus square root of 5 over 2. Okay, 2 different eigenvalues for a 2 by 2 matrix. That means the matrix can, in fact, be diagonalized because we'll get 2 one eigenvalue for each of those, one eigenvector for each of those eigenvalues. And as we know, the eigenvectors for different eigenvalues are going to be linearly independent. So that means we get two linearly independent eigenvalues altogether. So that's the basis of R2. Right? So that means at this point, we already know A can be diagonalized. Oh, sorry, diagonalized. But of course, we also want the eigenvector. So we want to explicitly compute that diagonalization, and we want the transformation matrix. So we still have to go on. And we need to compute the vectors. So let's see. First, let's compute the eigenspace for the eigenvalue lambda1. So that is the kernel of A minus lambda1 I2, or the kernel of 1 minus lambda1, 1, 1, and minus lambda1. I'll try to keep this on an abstract level as long as I can to avoid writing those ugly numbers here. So first thing I need to do is, or I can do is, I can easily turn this here into a 0. So I'm kind of reversing the usual process because that seems not so nice. I'd have to swap those rows first and so on. So let's rather do this, turn this into a 0 here. And I can simply do this by adding lambda1 times the first row here. So that yields the kernel of 1 minus lambda1 and 1. First row is not altered. For the second row, I get 0 here. That's what I wanted. And I get a 1. Now, if I look at this, lambda1 times the first row, I'll have plus lambda1 minus lambda1 squared here. So that's 1 plus lambda1 minus lambda1 squared. Okay, and if you look back at our characteristic polynomial, one plus lambda1 minus lambda1 squared. You notice this is almost the same. I just have to take out a minus sign, right? So this here is the same as minus lambda squared plus lambda plus 1. Sorry, minus lambda squared, of course. Yeah. And that blue expression is exactly the one I have here. And I do know that lambda1 is a root of the characteristic polynomial. So that is 0. And that makes the things a little easier here. So what I have is the kernel of this matrix here with a 0 row. And of course, I did fully expect to get a 0 row, because otherwise I wouldn't get a valid eigenvector. So that has to happen at some point if I'm doing this correctly. So I can now write down the eigenspace. That's going to be the span. Now let's see how I'm going to do this. Let's say I fix the x1 coordinate to 1. If I do that, then I have to fulfill this first equation here. This first equation is x1 times 1 minus lambda 1 plus x2 is 0. So if I fix x1 to 1, then that means I have to fix x2 to minus 1 plus lambda 1. Right, like this here. So that's the span I'm getting here. Or in other words, let's finally substitute the correct value for lambda 1. So we get actual numbers here. I need to do 1. And if I substitute lambda 1, remember that was 1 plus square root of 5 over 2. Basically, I have lambda 1 minus 1 here. So what I get is, instead of 1/2 plus square root of 5 halves, is minus 1 over 2 plus square root of 5 over 2. So I get minus 1 plus square root of 5 over 2. Or if we want to get rid of that fraction, we could change that to multiply that whole thing by 2, and then I get 2 and minus 1 plus square root of 5. So that's one eigenvector, the eigenvector corresponding to the eigenvalue lambda 1. I'll take a little shortcut for the second one. Basically, the computation is absolutely the same, or almost the same, just with lambda 2 instead of lambda 1. And if I do this, I get almost the same result. You can do this for practice at home, or you can just read up on the whole computation in the suggested solutions afterwards. The result will be, I get minus 2 and 1 plus square root of 5. So this is the eigenspace for lambda 2. And that means my transformation matrix let's call it S, is given by 2 minus 1 plus square root of 5 and minus 2, 1 plus square root of 5. And if I apply that transformation to my matrix A, meaning multiply S to the minus 1 times A times S, so I transform that linear mapping to the basis given by these two eigenvectors, then I get the diagonal matrix that consists of those two eigenvalues, lambda 1 and lambda 2. Or if I again put in the numbers, that is 1 plus square root of 5 over 2, 0, 0, 1 minus square root of 5 over 2. Like this, right? So let's call this D. That's our diagonal matrix. So A can be diagonalized, and this here is the diagonal matrix. Any questions about this so far?
Still no questions.
Still someone listening?
I mean, there's people here, so yeah, let's hope.
Hopefully. So final step, we do have the transformation. So the goal is now to compute a to the power of n minus 1 for any a that you want to give me. How do I do that? Well, we do know already that s to the minus 1 as is a diagonal matrix D. So we can solve this equation for a. We have to multiply it by s on the left and s to the minus 1 on the right. So we get a is s times d times s to the minus 1. What that means now, if we compute powers of a to the n minus 1, that's the same thing as computing the corresponding power of this whole expression here, s times d times s to the minus 1 times n to the power of n minus 1. And taking something to the power of basically means multiplying it, in this case, n minus 1 times. So what we do here is we take this expression, s times d times s to the minus 1. We multiply that by s times d times s to the minus 1, and so on. And we do this n minus 1 times. Now, if you look at that expression, you should recognize the following. What happens here is, you know that matrix multiplication is associative. So basically, it doesn't matter if we compute SD first and then multiply with all the rest, or maybe compute s to the minus 1s first and then multiply with SD on the left and this on the right. We can start with whatever we want. We cannot change the order of those matrices, so we couldn't, instead of SD, we could not compute DS. It's not commutative. But whether we start with this, or maybe with this, doesn't matter. So in particular, we can start by, let's keep SD on the left. Then we have s to the minus 1s. Let's start by computing that because that's easy. Then we again have a d. Then we have an s to the minus 1, and here next would come an s again. So again an s. Again, let's compute that right away because that's easy, and so on until we get to this last s here. Again, there's an s minus 1 in front of that. And then we have a d and an s to the minus 1 at the end, right? So this here, that's the end. This is the beginning. And for everything that happens in between, we always group these two matrices, s to the minus 1 and s together. The matrix multiplied by its inverse, well, that's of course the identity matrix. So we get SD times the identity. Times the identity, times D, times the identity, and so on. Times the identity, times D, times s to the minus 1. Multiplying by the identity doesn't do anything, so we can as well forget about that. And that means what remains is this s here at the beginning, the s to the minus 1 at the very end, and in between we have a total of n to the minus 1 d's, right? So all of that is d to the n minus 1. Now D is a diagonal matrix, and if you multiply a diagonal matrix by itself, right? So remember D is that form here. So D squared, for example, would be this matrix times itself. If you multiply that, you get lambda 1 squared, 0, 0, lambda 2 squared. So in particular, it's easy to compute D to the power of n minus 1. That's just lambda 1 to the n minus 1, 0, 0, lambda 2 to the n minus 1. And that helps us to compute this a to the n minus 1, right? So what we have to do is we have to compute this, that's easy, and then just apply the transformation. So we apply s times d to the n minus 1 times s to the minus 1. So we get, well, s, we know s already. That was, let's have a look. It was 2 minus 1 plus square root of 5 minus 2, 1 plus square root of 5. That was s here. Then we have this d to the power of n minus 1. That's not so hard. We have n plus square root of 5 over 2 to the power of n minus 1, 0, 0, and 1 minus the square root of 5 over 2 to the power of n minus 1. And I'm running out of space. Let me just move this a little. Hopefully I can fit in s to the minus 1. Actually, I don't even need to fit in s to the -1, but yeah, let's do that anyway. So s to the -1, that can also easily be computed. That's 1/4 square root of 5 times 1 plus square root of 5, 2, 1 minus square root of 5, 2. Yeah, you can easily do this by the inversion formula for 2x2 matrices, for example. And of course, we can do this computation. And then finally, get a formula for the fn's. Remember, fn-gn was a to the n-1 times f1g1, and f1g1, that was 1, 0. So in particular, I mean, we don't really need gn, we only need fn. So in particular, we could just take this whole thing, multiply it by 1, 0, and then just take the first row of whatever remains. And if you do this, the result that we get is the following. I'll just write it down in a slightly simplified way. So this is the formula we get here. Looks a little complicated with the square roots in it, but it's something that we can easily compute explicitly. So whatever n you want to know, you can just enter it here in that formula. Do your computations, you'll get the nth Fibonacci number. So even though we define that recursively, we now have an explicit formula for computing F2021, for example. And the surprising thing is, I think, even though that formula contains lots of square roots, looks pretty complicated, the result will always be an integer. We know that through the recursive definition, it can only be integers, right? So we get an explicit formula, and even though it looks strange, it will always yield an integer. We know that. And we obtain that formula not directly by manipulating the recursive definition, but through our knowledge about matrix diagonalization. So sometimes it pays off to convert your problem into something that looks very differently at first sight, but then offers you some nice tools that you can apply to get more insight into the problem. That's one such example here. So questions about this one or anything else?
So there was one question about the computation for the eigenspace of lambda 1, and it was not 100% clear how you got the 0 row. So not why it should be how it
little. So here we are. Okay, so first, this here, I'm just adapting my manipulation so that I get a 0 here, right? I'm adding lambda 1 times the first row, so lambda 1 times 1 minus lambda 1 is going to be 0. This one here yields this term here, minus lambda 1 squared plus lambda 1 plus 1. And we notice that this is pretty much the same as this expression here. Yeah, we have minus lambda 1 plus lambda 1 plus 1. And we obtained lambda 1 and lambda 2 as the roots of the characteristic polynomial. So what we have here is exactly, sorry, I want to do this in blue. It's exactly the characteristic polynomial evaluated at lambda 1. Now lambda 1 is a root of PA, so that means the value is going to be 0. That's the trick. Okay, I hope that clarified this idea here.
And then there is another question. Why doesn't the identity matrix matter for the computation?
Any matrix times the identity matrix is that same matrix. Yeah? A times identity is A. D times identity is D. So we can just forget about identities. Same as multiplying a real number by 1.
Okay, and then there's a question Could you explain again how you took out A's on 3A?
On
100%.
3A, let's have a look.
Ah, okay.
This one here, I'm guessing. Yeah. Okay. So what I did is I have this recursion formula here. So that's the formula that holds. We derive this from the one-dimensional recursion. Remember, we got that one here, right? So that's where we started. Then we basically used our 1D recursion to get that formula here. And that is the formula I'm using. I'm starting with applying it once to Fngn. Then I'm taking this vector here and apply the recursion formula to that. What I get is A times, and then I have to lower the indices by 1. So instead of n-1, I get n-2. Right? So recursion formula applied to that vector yields this result here. And again, matrix and matrix vector multiplication is associative. So instead of multiplying A with that blue thing here, I could as well multiply A by A and then multiply the result by the vector. So that's what I do here, right? I have A squared times this vector here. And now, again, I'm applying the recursion formula to this vector here. So that's the same thing as this by the recursion. And again, I'm regrouping. I'm putting that A with the A squared first, and I have this vector here. And I just repeat that process until I end up with F1G1 at the end. And to do that, I just have to repeat that process n-1 times. Right? Because to get from n to 1, I need to do this n-1 times. That's where the A to the n-1 comes from.
So different question. How did you immediately know what S inverse looks like?
How did I know what S inverse looks like? Where did I do this? At the end, right?
A little bit up, right?
Yeah, here it is. Yeah. So basically what I did here is if I have a matrix, let's call it, well, let's call it S, why not? Let's call it S. We have S11, S12, S21, S22, general matrix, 2 by 2 matrix, that's important. Then I can compute the inverse as 1 over the determinant of S. And then what I have to do is I switch the entries on the diagonal. So I put S22 here, S11 here. Yeah, I take these two, I switch their positions. And for the off diagonal elements, I invert their sign. So instead of S12, I write minus S12 and minus S21. And that's exactly what is happening here. I have this matrix here. I switch these two. So here's the 1 plus square root of 5. Here's the 2. And for this, I invert the sign. That's the plus 2. And for this, I also invert the sign. Now it's 1 minus square root of 5. And then I need to compute the determinant here. And that turns out to be 4 times square root of 5. That's how I got this. And remember that formula only works for 2 by 2 matrices. Right? So that's a little shortcut for 2 by 2 matrices, not for larger matrices, please.
Okay, next question. Could you explain again why G1 is the predecessor of F1 in the Fibonacci sequence?
Basically, that's because that's how I set it up. So let me scroll back here. Okay, so basically I want to somehow get this equation into this matrix vector form. And I do that by defining this second coordinate GK in addition to FK. Right, so I'm having a vector of 2 coordinates. And what I'd like is in the first row, I'd like to model this equation. So in the first row, I need access to FK, the current value of the first coordinate and the previous value of the first coordinate. So I want to set up this thing such that this first coordinate is the kth Fibonacci number. And that second coordinate should be the predecessor of the kth Fibonacci number, because that's the information that I need in order to actually model this equation. I want to set it up in that way, right? So that's why I define my FKGK in that way and then hope that I can actually make this work. Making it work in the first column is not a problem because that's how I set it up. I just define this as FK plus GK. I just need to make sure that GK is actually what I want it to be. It has to be the predecessor of this coordinate here, right? At all times. So GK plus 1 has to be equal to FK. And now let's just define the recursion in the vector such that this works. And I do have the information of FK here in the vector, so I can actually do that. Right? So basically, it's just a clever definition. I set it up because I will need those two values here, not just the FK, I also need the predecessor. So I need a vector of two coordinates that model the value and the predecessor. I just need to make sure that that value is really the predecessor. That happens in this equation here.
Okay, another question. So how did we go from deriving a to the power of n-1 to getting the explicit formula?
How do we go about this? So basically, where is it? Right, so we found out this here was the way to compute a to the power of n-1. And now remember, for the explicit formula, fngn, this is the equation we came up with in the first part in A, right? Fngn is a to the -1 times f1g1. That could easily be confused with an n. And f1 is 1, g1 is 0 by definition of the start of our recursion. Yeah, basically that is f1, the first Fibonacci number. And that here is g1, that's the 0th Fibonacci number. Okay, so that's what I need to compute. Well, I do know how to compute a to the n-1, right? So fngn is, let's combine all this here. So a to the n-1 is this expression. Sorry. So I want s d to the n-1, s to the -1, and then I need to multiply this with the starting value 1, 0. And I'm just doing the computations here. I'm computing this result, and then I get a vector that consists of two coordinates. The first coordinate is going to be my fn. That's the value I want. And the second coordinate is going to be my gn. That's the value I'm not interested in. I just needed that as an auxiliary construction. So I do this computation, and from the resulting vector, I just take the first row, the first coordinate. And this is, if you go through all the computations, you get this one here.
And that's the last question I can see.
Okay, wonderful. So we almost finished on time today. So thanks for your attention. Thanks for your questions. As usual, I hope to see you next week. And again, do attend the tutorials on Thursdays. We start at 2 o'clock and we'll be available until 5 o'clock each Thursday. You're welcome to ask any questions you want during the tutorials. And we usually have enough tutors to cater for everybody's needs there. So I'll be happy to meet you there as well. Good. Thanks a lot to Alan for doing the moderation again. And I'll also see you on Thursday.